A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
My Weird Prompts is a community-driven initiative exploring how AI can fuel curiosity and uncover the fascinating ways our world works. GPU compute for this podcast is generously provided by Modal. Learn more at modal.com.
Imagine for a second that you are trying to read a 1,000-page novel, but there is a catch. You can only see one single word at a time, and the moment you move to the next word, the previous one starts to fade from your memory. By the time you get to page 50, you have a vague sense of the plot, but you have completely forgotten the specific foreshadowing from page 1. That was the state of artificial intelligence for decades. It was a sequential slog through the mud. But then, in June of 2017, everything changed. We stopped looking at the world through a straw and started seeing the whole picture at once.
That is a perfect way to frame it, Corn. I am Herman Poppleberry, and today we are diving into the engine room of the modern world. Today's prompt from Daniel is about the transformer architecture, the foundational technology that turned the sequential bottleneck into a parallel processing powerhouse. We are going to trace this from the original, "Attention is all you need" paper, all the way to the massive developments we have seen this month in March of 2026.
It is wild to think that a single research paper from 8 people at Google basically retired an entire generation of AI models overnight. Before we get into the nuts and bolts of how these things actually work, we should probably talk about the before times, because you cannot really appreciate the transformer unless you understand how painful things were with recurrent neural networks and long short-term memory models. If you were working in AI in 2016, you were basically fighting a constant battle against time and memory.
The struggle was very real. Before 2017, if you wanted to process language, you used recurrent neural networks, or RNNs. The architecture was strictly linear. To understand the 10th word in a sentence, the model had to process words 1, then 2, then 3, all the way up to 9. It carried a hidden state, like a little backpack of information, from one step to the next. The problem was that as the sentence got longer, that backpack got heavier and the information inside got blurry. This is what researchers called the vanishing gradient problem. By the time the model got to the end of a long paragraph, it essentially forgot how the sentence started because the mathematical signal had decayed to almost nothing.
It was like a game of telephone, played by a model with a 5-second memory. If you had a sentence like, "The cat, which had escaped from the house earlier that morning after the mailman left the gate open, sat on the mat," an old RNN might forget that the subject was a cat by the time it reached the verb sat. It might think the gate sat on the mat or the mailman sat on the mat. It was incredibly inefficient because you could not use the full power of modern hardware. You had to wait for word 1 to finish before you could even start word 2. Your expensive GPUs were basically idling 90% of the time.
That lack of parallelization was the death knell for RNNs once datasets started getting massive. You could throw 1,000 GPUs at the problem, but if the architecture forces you to work word by word, those GPUs are just sitting around waiting for their turn. The transformer, introduced by Ashish Vaswani, Noam Shazir, Nikki Parmar, Jakub Luskoreit, Leon Jones, Aidan Gomez, Lucas Kaiser, and Ilya Polasukin, threw that entire linear approach in the trash. They realized that you do not need recurrence to understand sequence. You just need attention.
Attention is all you need. It is one of those rare instances where a paper title is actually an accurate summary of the revolution. It is also worth noting where those 8 authors are now, because they have basically shaped the entire industry. Ashish Vaswani is the CEO of Essential AI. Noam Shazir, who is a key contributor to multi-head attention, co-founded Character.ai. Aidan Gomez is running Cohere. These people are the Oppenheimers of the 2020s. So, let's break this down for everyone. We will go through 3 levels of depth here: starting with the foundational view for the general listeners, then moving to the professional level for the tech workers, and finishing with a deep technical dive into the math that makes it tick. Herman, give us the foundational view from 30,000 feet version.
At the most basic level, imagine you are looking at a full page of a book. Instead of reading it word by word, your eyes can dart around. If you see the word he on the last line, your brain instantly connects it to the name John mentioned 3 paragraphs up. You are not reading linearly, you are looking for relationships. The transformer does exactly that. It looks at every word in a sentence simultaneously and calculates how much attention each word should pay to every other word. It creates a map of relevance. If the model is processing the word bank, it looks at the surrounding words. If it sees river and water, it knows we are talking about geography. If it sees money and interest, it knows we are talking about finance. It sees the context all at once.
It is the difference between a flashlight and a floodlight. The RNN is a flashlight moving slowly across a dark room. The transformer is a floodlight that illuminates everything, letting you see how the chair relates to the table and the door simultaneously. It is about global context rather than local sequence. Now, let's step it up to the professional level. If you are working in tech or automation today, you are likely interacting with these models through an API or a local deployment. What is happening under the hood in a sequence-to-sequence context?
For the professionals, the transformer is a parallelizable sequence-to-sequence model. It is composed of 2 main parts, an encoder and a decoder. The encoder takes the input sequence, like a sentence in English, and maps it into a continuous representation, which is basically a massive, high-dimensional mathematical space where the meaning of the words is preserved relative to each other. Then, the decoder takes that map and generates an output sequence, like the same sentence in French, 1 token at a time. The key advantage here is that during training, the model can see the entire input sequence at once. This allows for massive parallelization on GPS because you're doing matrix multiplications instead of sequential loops.
But there is a catch at this level, right? The scaling problem. We hear about big O notation all the time in software engineering. How does the transformer handle long sequences?
That is the professional reality we are dealing with right now, especially here in 2026. The computational cost of the attention mechanism scales quadratically with the length of the sequence. We call this the O of n squared hurdle. If you double the length of your input, the work the model has to do quadruples. If you triple the length, the work increases 9-fold. This is because every single token has to compare itself to every other token. If you have 1,000 tokens, that is 1,000,000 comparisons. If you have 1,000,000 tokens, that is 1,000,000,000,000 comparisons. This is the primary reason why context windows were so small for so long, and why the industry is currently pivoting toward the hybrid models we will talk about later.
That quadratic scaling is the wall everyone has been hitting. But before we get to the modern shortcuts, we have to talk about the actual technical mechanics. This is for the math nerds and the developers who want to know what is actually happening in those layers. Herman, walk us through multi-head scaled dot product attention.
This is where the magic happens. Every word or token in an input sequence is first converted into a vector, which is just a list of numbers. But a word's meaning changes based on its position. Since the transformer doesn't process words in order, it needs a way to know where each word sits. The researchers solved this with positional encoding. They use sine and cosine functions of different frequencies to add a unique mathematical timestamp to each word vector. It is like giving every word a unique coordinate in time, so the model doesn't get confused when it sees the same word twice in different places.
I always found that part elegant. It is like a musical signature for every position in the sentence. So once the model knows where the words are, how does it actually pay attention?
For every token, the model creates 3 different vectors: a query, a key, and a value. Think of it like a retrieval system or a file cabinet. The query is what the word is looking for. The key is the label on the file folder. And the value is the actual information inside the folder. The model calculates a score by taking the dot product of the query of one word with the key of every other word. This tells the model how much attention word A should pay to word B. Those scores are scaled down by the square root of the dimension of the keys to keep the math stable, and then passed through a softmax function to turn them into probabilities that add up to 100%. Finally, you multiply those probabilities by the value vectors to get the final output for that layer.
And the multi-head part just means the model is doing this multiple times in parallel. Like having 8 different people look at the same sentence, where one person is looking for grammar, another is looking for sentiment, and another is looking for factual entities.
Each head can focus on different types of relationships. One head might be great at linking pronouns to nouns, while another might be focused on verb tenses or technical jargon. After the attention phase, the data goes through a position-wise feed-forward network, which is basically a standard neural network layer that processes each position independently. You stack these layers on top of each other, usually 6 to 12 in the original paper, but hundreds in the models we use today like Claude or GPT. Between each layer, there are residual connections and layer normalization to keep the signals from degrading as they move deeper into the neural cathedral.
It is a massive, complex machine, but at its heart, it is just a bunch of dot products and matrix multiplications. What is truly wild is how this architecture, which was originally designed for language translation, turned out to be a universal pattern matcher. It works for images, it works for proteins, it works for music. Why did this specific design unlock so much across different modalities?
It comes down to the fact that the transformer makes no assumptions about the structure of the data. An RNN assumes data is a sequence. A convolutional neural network assumes data is a grid, like an image. But a transformer treats everything as a set of relationships. If you can turn something into a token, whether it is a pixel, a DNA base pair, or a musical note, the transformer can find the patterns. It is a general-purpose computer for high-dimensional data. And because it is so parallelizable, we were able to scale it to the point where emergent properties started appearing. We found that if you make the model big enough and feed it enough data, it doesn't just predict the next word, it starts to reason about the underlying logic of the world.
Which brings us to the core concepts of encoding and decoding. We touched on this, but it is worth a deeper breakdown because this is where the generation happens. The encoder is the understanding phase. It builds that high-dimensional map where every word is contextualized by every other word. If the encoder does its job, the model has a deep, nuanced concept of what the input means.
The decoder is where the creative part happens. It is an autoregressive process, meaning it generates one token, then feeds that token back into itself to generate the next. But there is a clever trick called masking. During training, when the model is learning to predict the next word, we don't want it to cheat by seeing the words that come after the one it is currently predicting. So, the decoder uses masked self-attention to hide the future tokens. It can only look at what has already been generated. It also uses something called cross-attention, where it looks back at the encoder's map to make sure the words it is generating actually align with the original input.
It is like a translator who has a perfectly annotated map of the original text on one side of their desk, and they are writing the translation on the other side, word by word, constantly checking the map to make sure they haven't lost the thread. But Herman, we have to address the misconception that these models understand language like humans. They don't have a soul or a consciousness. They are mapping high-dimensional statistical relationships.
That is a crucial point. They are incredibly good at predicting the next most likely token based on a trillion-parameter map of human thought, but they are not thinking in the way we do. However, as of yesterday, March 24, 2026, the line between statistical mapping and actual logic got a lot blurrier. A landmark paper was released that established a formal mathematical equivalence between sigmoid transformers and Bayesian networks. Researchers proved that these models are actually implementing something called loopy belief propagation.
Wait, explain that for the non-math PhDs. What does loopy belief propagation actually mean for the average user?
It means that the transformer isn't just guessing. It is performing a formal type of probabilistic inference that is used in advanced logic and physics. The paper proved that these architectures are, in fact, Turing complete. This means that, given enough memory and time, a transformer can compute anything that any other computer can compute. It solidifies the transformer as a fundamental piece of computer science history, not just a trendy machine learning trick. It explains why we are seeing such a massive jump in reasoning capabilities in models like GPT 5.4.
Speaking of GPT 5.4, the reports from March 5th were insane. We're talking about an extreme reasoning mode and a 1 million token context window. Anthropic's Claude Opus 4.6 just hit that 1 million token mark as well. But we keep coming back to that O of n squared problem. How are they hitting 1 million tokens without requiring a nuclear power plant for every query?
The industry is pivoting toward sparsity. This is the big shift from dense models to sparse models. Look at DeepSeek v3, which has been the talk of the industry lately. It is a mixture of experts, or MOE, architecture. It has a staggering 671 billion total parameters, but only 37 billion are active for any given token. Instead of every word hitting every single neuron in the model, a router sends the token to a specific set of experts that are best suited for that task.
It is like having a giant hospital where, if you have a broken leg, you only see the orthopedic surgeon, not the entire staff of 500 doctors. It saves an incredible amount of energy and compute time. But even with MOE, we are seeing the limits of the pure transformer. That is why everyone is talking about hybrid models lately. We are seeing models like Jamba and the new Qwen 3 next that are blending transformer attention with state space models like Mamba.
The goal there is to get the best of both worlds. State space models, or SSMIS, scale linearly. Big O of n. That means if you double the input, you only double the work. They are incredibly efficient for long sequences, but they haven't historically been as good at the deep reasoning and pinpoint retrieval that transformers excel at. By interleaving transformer layers for the heavy lifting and SSM layers for the sequence handling, these hybrid models are finally cracking the code on massive datasets without the n-squared penalty. It is the most significant architectural shift since 2017.
It feels like we are in the optimization era of the transformer. The first 5 years were just about making them bigger. Now it is about making them smarter and more efficient. But the stakes have also moved beyond just research papers. The geopolitics of these architectures are getting intense. We have seen this standoff between Anthropic and the Pentagon this month over usage restrictions on autonomous warfare. Because Claude is so capable, the government wants to use it for things that Anthropic's safety guidelines explicitly forbid.
It has led to this bizarre situation where a private AI company is being designated as a supply chain risk by certain factions in the government because they won't let the military use their attention heads for targeting. This is happening right alongside the White House's new AI policy framework that was announced earlier this month. They are trying to preempt state-level safety laws, like the ones in California, because they are worried that too much regulation will stifle the development of these next-generation architectures and cost the U.S. its global dominance.
It turns out that whoever has the most efficient attention mechanism effectively has the best intelligence infrastructure in the world. It is a new kind of arms race, and it is not just about the big models. We also had that Moonshot AI paper on March 16th introducing attention residuals, or AttenRes. For years we've used simple residual connections where you just add the output of a layer to its input. But AttenRes allows layers to look back at the raw attention scores of much earlier layers directly.
That is a massive deal for long context performance. It helps with the middle of the context problem where models tend to forget details that are buried in the center of a long prompt. If you are a developer, this is the kind of stuff you need to be tracking. We are moving from RAG, or retrieval, augmented generation, where you feed the model small snippets, to long context workflows where you just give the model the whole bucket of data.
So, if you are a listener trying to make sense of all this, what are the practical takeaways? First, understand that context is the new currency. A 1 million token context window means the attention of the model can now span entire codebases, or a dozen different textbooks at once. Second, keep an eye on the inference era. For a long time, we cared about how long it took to train a model. Now, it is all about inference speed and cost. This is why the shift to sparse MOE models and hybrid architectures matters to you. It is what makes the AI on your phone or your laptop snappy instead of laggy.
And finally, don't get too attached to the word transformer as the only game in town. While it is the king right now, the move toward Turing, complete sigmoid models, and hybrid SSMIS suggests that the architecture is still evolving. We are moving toward agentic AI, where these models don't just talk to you, but they use their understanding map to navigate the web, write code, and solve multi-step problems. We covered that transition in episode 1500, Beyond the Chatbot, which is a great follow-up to this technical deep dive.
It really is the multi-surface operating layer we have been talking about all year. The transformer was the spark, but the fire is spreading to every corner of computing. It is no longer just a weird prompt thing. It is the fabric of how we interact with information. Herman, any final thoughts on the Turing completeness proof? Does that change how you view these models?
It makes me more optimistic, honestly. For a long time, there was this black box stigma. People said we don't know why they work, so we can't trust them. But as we peel back the layers and find these formal mathematical structures, we are realizing that these models aren't just stochastic parrots or random guessers. They are implementing sophisticated probabilistic logic. We are basically discovering the math of intelligence rather than just inventing it. It is a very exciting time to be a nerd.
A very exciting time to be a donkey and a sloth, too. I think we have covered the full spectrum today, from the sequential bottleneck of 2016 to the Turing-complete reasoning of 2026. If you want to dive deeper into the research landscape that led us here, check out episode 1111, The Architecture of Intelligence. And if you want to see where this is going next, episode 1479 on the speed of thought is a must listen.
And if you found this deep dive helpful, we have an entire archive of over 1,500 episodes exploring the nuances of this revolution. You can find everything at myweirdprompts.com, including our RSS feed and all the ways to subscribe.
Big thanks to our producer, Hilbert Flumingtop, for keeping the wheels on this bus. And a huge thank you to Modal for providing the GPU credits that power our research and this show. Without those H100s, we would still be stuck in the sequential bottleneck.
If you are enjoying the show, a quick review on Apple Podcasts or Spotify really helps us reach more people who are curious about how this world is being rebuilt. We will be back soon with another prompt from Daniel.
This has been My Weird Prompts. We will see you in the next one.
See you then.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to our show.